It's my pleasure to introduce Fenglong You from the University of Oslo, who will talk to us about the generations, vibrations, and mirror symmetry.
Okay, thank you so much for the invitation. And yeah, my title here has three things: degeneration, vibration, and mirror symmetry. And to put them together, I can state my title as degeneration is mirror to vibration. So that means the general principle in here is that if we have a degeneration of a variety on one side, on the mirror side is to have some vibration structures. And under this principle, so for example, if we have a variety X, let's say glabial, and degenerate into two pieces, we can study, on one side, we can study symplectic geometry of X and see how this degenerate, how this changes under degeneration and how's that related to symplectic geometry of two pairs, X1D and X2D. And on the other side, we can study the complex geometry of the mirror and study the relation of this with the complex geometry of the mirror of two pairs under this some vibration structures. To be more precise, what I want to talk about here today is this diagram here. So this diagram in general, like when you study mirror symmetry, we can study different things. We can study like categories, but in here, I think it's more suitable to study this more classical version of mirror symmetry, which is relating chromophytic invariance with periods. Like for example, because like when we talk about pairs, I don't think like there's a definition of a Fukaya category for a pair, so it's more difficult to study. So right now, I just talked about the enumerative mirror symmetry part, which means first we have chromophytic invariance of X. By mirror symmetry is related to some period integral of the mirror, and under degeneration, this chromophytic invariance of X is related to chromophytic invariance of two pairs, and there is a version of relative mirror symmetry that can relate relative chromophytic theory with relative pairs, and there is a way to relate these periods and relative periods under this vibration structure. So everything here can be defined if we think about chromophytic theory and periods. So the goal for today is to go through this diagram, and some part of this diagram is classical, like the relation between chromophytic invariance and periods. This is the classical mirror symmetry that has been proved like 25 years ago, and the relation between chromophytic invariance and relative chromophytic invariance that has also been known like for 20 years. What's more recent is like relative mirror symmetry and the relation between periods. So first, I will briefly talk about this on the horizontal line above here, which is the chromophytic invariance and periods. So this is a classical story. First, we need to define a Chromosome invariance. To define that, we consider a moduli space of maps, of stable maps from curve to with some markings to the target variety X. This is also called a conservatory space. It's called a moduli space of stable maps. The degree D here means the push forward of the fundamental class of the curve. Stable means its automorphisms of the map is finite. Chromosome invariants are defined as intersection numbers on this moduli space. And so we can define some cohomology classes on this moduli space. For example, we can define the cohomology classes by pullback of this evaluation map. This evaluation map maps this map to the image of this map. And so we can pull back some cohomology classes from X, and we get some cohomology classes on the moduli space. There is another type of cohomology class on the moduli space. It's called a descending class, which is the first term class of a line bundle. And this line bundle has fiber, which is the contingent space of the marking. So we have n markings, we have n descending classes. With these two kind of cohomology classes, we can use these cohomology classes to intersect with the fundamental class of the moduli space to get a number, and that number is called Chromosome invariant. And yeah, an invariance will be 0 unless it satisfies the virtual dimension constraint, which means the virtual dimension of the moduli space equals the sum of the degrees. For example, if we consider quinty threefolds, then the general 0 quinty threefolds with no markings, then the virtual dimension is 0. And this invariance gives a virtual count of degree D rational curves in quinty threefold. So that's the definition for Chromosome invariance. Yeah. So let me know if you have some questions. And so yeah. So for the statement of mirror symmetry, it's a relation between a generating function of general 0 Chromosome invariance and some period integrals on the mirror. And it can be stated like this: generating function called J function equals period integral, which is called an I function. This under something called mirror map, and this J function looks like this. For example, for quinty threefold, this J function is a generating function of 1 point general 0 Chromosome invariant, and so general 0 1 point degree D Chromosome invariant, and this denominator here should be understood as this under this expansion as sum of these positive powers of psi descending classes. So the precise form of this function is not so important here to understand the talk. It just means that on one side we have generating function of Chromosome invariant, and that's related to some hypergeometry series. Like in quintic, for quintic threefold, it's the I function is a hypergeometry series. Looks like this. It's much easier to compute. So we can use mirror symmetry to compute Chromosome variance because this function here is more like elementary. It's easier to compute. And the relation, as stated before, is the equality between a generating function of Chromosome variant and this hypergeometry series, and with some quotient by some normalization, which is the first term of this hypergeometry series. And this is the kind of statement for the classical enumerative mirror symmetry, and that has been proved for a lot of cases. And for this vertical line on the left, it's the degeneration formula that relates Chromosome variance with relative Chromosome variance. It's also known for a long time. And the definition of relative Chromosome theory is similar to the definition of absolute Chromosome theory. But here we have a variety with a divisor and with some tangency conditions encoded by these KIs here. And it's similar to an absolute Chromosome theory. We use this data to define a moduli space of relative stable maps. And so in here, we have two kind of markings. We have M plus N markings. The first M markings are relative markings that map to the that encodes the tangency conditions, and the last M markings are just regular markings that we see before in absolute Chromosome theory. And again, we can have evaluation maps. We have two types of evaluation maps in here. If we have relative markings, then we have evaluation map to D. And if we just have interior marking, then it just map to X. Then put back some cohomology classes, and then intersect with the virtual fundamental class, and we get an invariant. And again, for the invariant to be non-zero, we need to have this virtual dimension constraint. The virtual dimension of the moduli space equals the sum of the degree. The degeneration formula states that if we have a degeneration, that this, then the central fiber has two irreducible components. For example, if we degenerate quintic into a blow-up of P3 and a quartic, then the absolute Chromosome variant can be computed as sum of product of relative Chromosome variance of these two pairs. So this was proved about 20 years ago. It's also a classical story. So these two parts are classical stories, like Chromosome, the relation between Chromosome variance and periods, and the relation between Chromosome variance and relative Chromosome variance. And now this horizontal line here is more recent. It's called relative mirror symmetry. That relates relative Chromosome theory with relative periods. To prove relative mirror symmetry statement. In here, we usually like relative chromovision theory is difficult to study, and the approach in here is to use some orbifolds. So we consider an orbifold which is called root stack, which that has orbifold structures along the divisor D with stabilizers mu R, and we can change the tangency conditions into some orbifold conditions, and then relate relative invariance with orbifold invariance, and then we can study relative invariance from orbifold invariance, because this orbifold theory is absolute theory, so it's easier to study. In summary, the approach is that we can consider relative chromovision theory as a limit of certain absolute orbifold theory. And so this root stack XDR when R goes to infinity. The precise statement is that in general zero, this relative chromovision invariance will be the same as corresponding orbifold chromovision invariant of this orbifold when this R gets sufficiently large. So for relative mirror symmetry, if we know about mirror symmetry for this orbifold, then we can take a limit to get a relative mirror symmetry statement from the pair. But to do that, we first need to generalize this result a little bit more to get, like we define something called, we generalize the definition of relative chromovision theory to include more invariance, which we call relative invariance with negative content orders. And we can also prove a statement that relate this kind of relative chromovision invariance with the corresponding orbifold chromovision invariant. The reason to consider this is that that makes relative chromovision invariance easier to study, and this is a geometric picture of what it means for negative content orders, but it's not so important in here. If you are interested, then you can take a look, but it's not so important for the talk. And the reason to have this extra relative chromovision invariance that we can have a nice structure of relative chromovision invariance of relative chromovision theory, which allows us to stay relative mirror symmetry statement. And so, like, for example, there's a version of relative quantum cohomology ring. There's something called given transformer reason. In general, the enumerative mirror symmetry statement can be stated in terms of given transformer reason. And it's also related to the Chromosome program. For relative mirror symmetry, which we plan to talk about here, under this principle, relative invariance considered as a limit of orbifold invariance. And so we just need to study this orbifold, and the the enumerative mirror symmetry statement is about a generating function of chromosome invariance, a relative chromosome invariance with periods, and these periods are called I function here. So the question here is just about finding an I function, and an I function we can compute it for these orbitals by consider this orbital as a hypersurface in some P1R bundle, and that then use orbital quantum lattices and mirror theorem for toric stack bundles, and we get an I function for this orbital. It looks like this, and this J here is the J function for X. So if we know about the I function for X, then we can replace J by I of X, then we get some implicit expression, which is the relative period, which is the certain period for orbital, and take a limit, and we get relative period. And for this formula, we take a limit, we get as r goes to infinity, then we get I function for the pair. So mirror symmetry statement for the pair is this kind of function. It will equals to a generating function of this pair, chromosome invariance of this pair with some mirror map. That's called relative mirror symmetry. And this was for smooth pairs when D is smooth, but we can also generalize that to the case when the divisor is simple normal crossing. The story is similar to the smooth case. We can consider this orbital. It's called a multi-root stack, and when these roots are sufficiently large, this orbital invariance that becomes independent of R, and it has a limit, and this limit is, we defined it as a formal chromosome invariance of this infinite root stack. You can consider this as a chromosome theory for this simple normal crossing pair. If you know about log chromosome invariant, then this invariant is not exactly the same as log chromosome invariant, but it has some nice properties. It has all these nice structures, and we can use this to state a relative mirror symmetry for simple normal crossing pairs. So by similar argument as in the smooth case, we can find an I function for a simple normal crossing pair, then this is related to the chromosome invariant of this pair, and this is called a relative mirror symmetry for simple normal crossing pairs. So that is the story for this horizontal line. And so for this vertical line, it's maybe easier to understand. And before we talk about this relation between periods, let me remind you of the relation between mirror, a variety and its mirror. So if we have a Calabi-Yau X, then the mirror of this Calabi-Yau is another Calabi-Yau. But if we have a pair, smooth log club ER pair XD, and the mirror is Landau-Ginsburg model X jack and W, and W is called the superpotential. And if we consider the non-compact club ER, which means the complement of this smooth anti-canonical divisor, then the mirror of this non-compact club ER is this variety X check without the superpotential. You add the divisor D, then we add the superpotential. And also the smooth anti-canonical divisor D is mirrored to the generic fiber of the superpotential. Yeah, so for a generic T in C, then the preimage of the superpotential should be a mirror to this divisor D. So this is how mirror symmetry works for smooth pairs. Okay, and there's a conjecture that states if we have a degeneration of a club ER into two pieces. So X is a club ER degenerated into X1 and X2. Again, we can consider an example, which is quintet threefold degenerate into blow up of P3 and quartic. And in this case, we consider the mirror of these two pairs, which are Landau-Ginsburg models. We have W1 and W2 are superpotentials, and the generic fiber of W1 and W2 are mirrored to the same club D. And the conjecture by Duran, Harder, Thompson is that the Landau-Ginsburg models of these two pairs can be glued to the mirror of that original club ER. So we get X check, and this X check has a vibration structure over P1. So that was the picture that I mentioned in here. So if we have a degeneration, on one side we have a vibration, on the other side, if we have this kind of, it's called turbulent degeneration. If we have this kind of degeneration, the central fiber has two irreducible components, then the mirror will have a P1 vibration. Yeah, so that's the relation between degeneration and vibration that they conjectured. And you can study this conjecture for you can study this conjecture in different aspects. Like you can, for example, compute the Euler characteristic. It can be checked that it satisfies this mirror relation. This can also be studied by using SYZ mirror symmetry for elliptic curves. You can also try to study this conjecture for using the closed-Sieber program. What I want to talk about here today is slightly different. I want to talk about the periods. So, as stated before here, this periods of club ER is related to this Chromosome invariance, and relative periods is related to relative Chromosome invariance. And Now these chromophytin variants are related by degenerations, and what's the relation between their mirrors, and how does that relate to vibration structures? So in general, we can compute periods using the vibration structure. If we have a family of clavier, it's fiber by so if we have a family of clavier n-fold fibered by clavier n-1-fold, then the period of the family of clavier n-fold can be computed as a residual integral of the pullback of the period of the this clavier n-1-fold by a generalized functional invariant. This generalized functional invariance is defined in here, below here. So if the definition is that if we have a family of clavier and the morphism from the base of this family to the moduli space of the fiber is called a generalized functional invariant. So this so far it looks abstract, but it's actually, if we look at an example, then it's maybe easier to understand. Again, from the quintic case, the mirror quintic Q phi check is fibered by mirror quartic K3, and the holomorphic periods for mirror quartic K3 is explicit hypergeometry series that looks like this. Sum of D greater or equal 0 for D factorial over D factorial to the 4th Q to the D. And the generalized functional invariant in this case is just a rational function. It can be computed explicitly as this. The way to get to this rational function is that we can write down an explicit equation for mirror quintic, and we can also write down explicit equation for mirror quartic, and there is a map that can be computed, which is this. And so this mirror quintic has a vibration structure over P1, and the fiber is mirror quartic. And now using the period for mirror quartic and this function, we can compute the period for quintic, which is, so in here, we would replace this Q by lambda. Now this part is completely elementary. So we would replace Q by this rational function and expand this as a series like this. In here, we use an identity like 1 over 1 minus y to the k plus 1 equals sum of this d plus k factorial, d factorial, k factorial, times y to the d. Then we get this. Then we get this part here from this, and then we can cancel 4d1 factorial, and we get to this expression. And then if we take residual integral for the variable y, then the only thing left is the term with d1 equals d2. Then that gives the period for the mirror quintic. So the mirror quintic, the period for the mirror quintic can be computed as a residue integral of period of quantity K3, mirror quantity K3, and with this generalized function invariant lambda. And this variable y should be considered as the parameter for the interior vibration. So when we integrate out this parameter, we get the period for we get an external period, not an interior period. Yeah. And yeah, for the so that is the relation between the vibration and periods. And what we want to talk about is the gluing. So if we have a degeneration, and how do we relate relative periods with these absolute periods? There is an example. If we consider this Calabi-Yau threefold Q5 tilted, which is a complete intersection of pi degrees 4111 in P4 cross P1, and this is actually a conical transition of the quintic, and this has a degeneration into two pieces. And so X1 tilted is a hypersurface of pi degree 41 in P3 cross P1, and X2 tilted is a complete intersection of pi degrees 4011 in P4 cross P1. And these are complete intersections in total lattice, and everything about it is explicit. And the mirrors of these are also explicit. And if we write down the mirror equations, then we can compute the corresponding generalized functional invariance. And if you look at the expressions, this lambda 1, lambda 2 is just a factor of lambda. So if we have a degeneration, then the generalized functional invariance are related by a product relation. And like the quintic case, we know about this period for mirror quantity K3, and we know about the generalized functional invariance, so we can compute the period for this conical transition of quintic by a residual integral of this F0 of K3 by the generalized functional invariant with some prefactors, and compute this residual integral, then we get this period for this Q5 tilted, and this period that has appeared in many papers before, and that's how we can compute this period from the period of this K3. And we can also compute relative periods by just pull back this period by the functional invariance, and then we get these two periods for these two pieces. These are relative periods, and the relation between these periods is this formula. So there is something called hardman product. If we have two series, then if we have two series, this AN, QN, this BN, Q to the N, then the hardman product is just take the coefficients of the same power and then multiply them together to get another series. And it can be computed that we have this explicit relation. In here, you can think about y here as the base parameter for the Landau-Ginzburg model of x2 tilde, and 1 over y as the base parameter for the Landau-Ginzburg model of x1 tilde, and integrate them out, then we get this external period for this Calabi-Yau threefold. In general, if we have a degeneration of Calabi-Yau completenization in toric varieties, then we always have this kind of relation between their periods. And you can also have this kind of expression for the solutions of Picard-Fuchs equations. The basis of solution for the Picard-Fuchs equations are these I functions that we talk about for that's related to the Chromosome invariance. And so this periods, so in summary, this periods of x, of mirror of x is related to Chromosome invariance of x, and periods of d is related to Chromosome invariance of d, and these two relative periods are related to relative Chromosome invariance under this mirror symmetry. And that's the case for Calabi-Yau. Now, if we consider more general varieties, for example, fundamental varieties, in here, it's a slightly different from fundamental variety. It's called quasi-fundamental variety. It means that it has it's smooth. Its anti-canonical linear system contains a smooth Calabi-Yau member, and we also have phase equals 0. The examples are this. If we have a degeneration of Calabi-Yau into two pieces that we talked about before, and then these two pieces are quasi-fundamental varieties. For example, when we degenerate when we consider this example, like this x1 tilde and x2 tildes are quasi-fundamental varieties. We can consider degenerations of these quasi-fundamental varieties into two pieces. An example is that we can consider a degeneration of a quantity threefold into a product of P3 and a cubic threefold, and they intersect along a cubic surface. And for this, we can consider its mirror. So what's the mirror story of this degeneration? In this case, D is a cubic surface, which is not a Calabi-Yau. If we still want to consider mirror for this x1d and x2d, then that means the generic fiber of W is mirror to D. If we want to consider mirrors for, let's say, x1d, this is not a log Calabi-Yau pair. So in principle, we cannot talk about the mirrors of this. But if we actually want to think about the mirror of this pair when D is not Calabi-Yau, then we also want this generic fiber of the superpotential is mirror to D. And since D is not Calabi-Yau, the mirror of D is also a Landau-Ginsburg model. So for example, when D is funnel, like cubic surface, in that example, then the generic fiber of this W is also a Landau-Ginsburg model. So that means we talk about a Landau-Ginsburg model whose fiber is also a Landau-Ginsburg model. That means in this case, we should consider higher rank Landau-Ginsburg model. And the higher rank Landau-Ginsburg model is that we have multi-potential H1 to Xn, Hn mapped to Cn, and the generic fiber of the Landau-Ginsburg model is Landau-Ginsburg model of rank n-1. And yeah, so the generic fiber of the Landau-Ginsburg model of rank n is rank n-1 Landau-Ginsburg model. For example, rank 2 Landau-Ginsburg model for a simple normal crossing divisor D equals D1 plus D2, then we have H1, H2 that's mapped to C2. The generic fiber of H1 is mirror to D1, and yeah, it's mirror to D1 with its smooth anti-canonical divisor. And generic fiber of H2 is mirror to D2, and that is mirror to D2 with its smooth anti-canonical divisor. That's called a rank 2 Landau-Ginsburg model. Now the degeneration for quasi-funnel lattice that we talk about is actually a degeneration of X also with its smooth anti-canonical divisor. So we degenerate a pair XD, a log Calabi-Yau pair XD, to these two pairs X1 D0 plus D1, X2 D0 plus D2, and we group them together to a rank 1 Landau-Ginsburg model with a P1 fibrillation, and which is mirror to XD. So basically, the conjecture in here says that if we have a degeneration of a log Calabi-Yau pair, then on the mirror side, we have two rank 2 Landau-Ginsburg models, and we group them together to get a rank 1 Landau-Ginsburg model. And we can also compute the Euler characteristic, which may also satisfy this mirror relation. And similar to the Calabi-Yau case, we can also look at snap periods. In here, we can consider an example, which is Q4 tilted, which is a complete intersection of 3, 1, 1, 1 in P4 cross P1. And we can also compute their functional invariance. Again, they satisfy a product relation like this. It's similar to the Calabi-Yau case, but just that it's similar to the Calabi-Yau case. Now we can use this generalized functional invariance to compute relative periods for all of them, like For example, we can compute relative period for the Q4 tilde from the period of the D0, which is the intersection of two pieces. So the result is similar to the Calabi-Yau case. We have a hardman product relation with this residue integral. And now in this case, we have relative periods for pair XD and period for D0, D12. So D12 is the intersection of D1 and D2. And periods for these two simple normal crossing pairs. And that should give a relation. This relation between these periods gives a relation between the corresponding chromovision invariance. And this part, which I think I don't need to talk about. Yeah. And so in the end, the last thing that I want to talk about is that if we have a rank 1 Landau-Ginzburg model, this rank 1 Landau-Ginzburg model is the ordinary Landau-Ginzburg model. And the genetic fiber is Calabi-Yau in 1 dimension lower. Now, what is the rank 0 Landau-Ginzburg model? And rank 0 Landau-Ginzburg model is just a Calabi-Yau because it's the base of the Landau-Ginzburg model is just a point. So it's a Calabi-Yau vibration over a point. So it's a Calabi-Yau. And with this, you can consider the original conjecture by Duran-Harder-Thompson as growing 2 rank 1 Landau-Ginzburg models to a rank 0 Landau-Ginzburg model with a P1 vibration. In general, we can group 2 rank n plus 1 Landau-Ginzburg models to a rank n Landau-Ginzburg model with a P1 vibration. And so the original conjecture is just the rank 0 case of the more general conjecture. And we can also use this to study the iterating structure of the Duran-Harder-Thompson conjecture, which is when we degenerate Calabi-Yau into 2 pieces, we can further degenerate these 2 log Calabi-Yau pairs into 4 pairs. And in this case, for example, in a quintic case, that gives a elliptic vibration over P1 plus P1. So in general, the degeneration, if we have more complicated degeneration, we will have more complicated vibration. And if the dual intersection complex of the central fiber of the degeneration has dimension k plus 1, then the mirrors should have a vibration with k dimensional base. Yeah, and that's all I want to talk about today. Yeah, thank you.
Thank you. I know Fenglong has to leave. I don't know if someone has a pressing question.
In a few minutes, yeah.
Or if he really wants to wait till then. I do have a question which is very lateral. So this quasi-Fano varieties remind me a lot of a construction by Alex Seff that later was kind of improved and expanded by Corti, Nordstrom, Haskins, and Pacini to construct G2 manifolds. So they start with something that's sometimes a fan variety, but really what you want is a good K3 surface on it and matching with another fan variety and another K3 surface and some S1 bundle on top of it. Have you heard of this before? Or?
No.
No, that's okay.
I don't think so.
It's just ringing a bell to me that I think they work for this kind of problem. So basically they start with a fan of three, sorry, I should have said fan of threefold. Yeah, they start for something close to a fan of threefold, put an S1 bundle on it, and then remove a K3 surface and the bundle at that bit, and then just glue two of these guys together in a hyperkähler way. Yeah. I was just getting the feeling this reminds me a lot of this, but maybe I'm not. Maybe I'm not right. Yeah.
Yeah, maybe just I don't know about that font. So
maybe
it's related. Yeah.
To mirror symmetry.
Yeah. Yeah.
All right. Any other questions or comments?
Can I ask a question?
Yeah. Sure.
Yeah. So in the you mentioned that example of the mirror dual of a quintic threefold earlier, and you mentioned that it's a P-band family of K3 surface.
Yeah. Right.
Yeah. So I'm wondering what kind of the singularity arise on this special fiber of the K3.
I don't remember. There are some singular fibers. I don't remember what's the specific type of singularity that we have at the singular fibers. Yeah, I don't remember that. Yeah. There are some.
Your period is you have a period interval, so it's around that singular fiber to compute.
Yeah, in here, yeah, I compute the period. So this has this vibration. I compute the period from the period of this GLAB in one dimension lower. Yeah. Yeah. Just by the singular fibers are related to these functions. Yeah. This generalized functional invariant that gives the information for what kind of singular fiber that you have. Yeah, right. That precisely capture the information from the singular fibers.
Also, this I function and J function related by this transformation tau. And I'm wondering if this I and J functions are related to modular forms.
I don't know, but there are some generating function of Chromosome invariance that's related to the modular form, but I think it's a different generating function. I suppose it's not this J function. Yeah. Yeah.
Okay, thank you.
Any other comments, questions? Yeah. All right. Well, thank you very much, Fenglong.
Yeah, thank you for the invitation.